Welcome viewers. In this series of videos we are going to do the design of substation equipment foundation using Eurocode. So this is stage 1 out of 7. In this we are going to look at overview of calculations. So first we are going to do the design of single isolated footing. These are the various design stages which we are going to look as a series of 7 numbers. In the first that video series we are going to look overview of calculation. Second, foundation and soil parameter load and load combinations, followed by that stability check, foundation bolt design of bottom slab, and in the fifth stage we can see the punching and one-way shear for the bottom slab, and finally the design of pedestal is a 7th stage. So now let me look into that Excel calculation. So at the screen you can see the table of contents which is going to cover all these 7 series of our equipment foundation design calculations. So which including this introduction page which is going to explain what is the detailed calculations, which is what are the formulas we are going to follow for stability check, design of a bottom pad and foundation bolt, check for punching shear, one way shear, all those information we can see in the introduction part. And finally in the annexer part we can able to find out that images of output of the calculations including the reinforcement details. So overall this 22 page of calculation will cover the equipment foundation design calculations. Now we will look into that introduction part. Though in that introduction part we need to mention the purpose. This purpose is to design a open foundations for single foundation, single pedestal with 1.5 meter depth of foundations below finished ground level. Following are the load cases which we are going to consider: dead load, live load, conductor tension, wind load in X and Y, ice loads, short circuit forces. So these are the 7 forces which we are going to consider in foundation design. And for the SLS load combinations, these are the load combinations. There are 5 load combinations we are considering, that including ACF combinations. For ULS load combinations we are considering as per table A12A and B of class 6.4.3.2 of EN 1990. These are the equations under that class. However, for short circuit force there is no straight explanation in this code. It is mentioned as accidental load combination, so we have considered that accidental load combinations here. And foundation stability check start from these 3 main checks. One is check for bearing pressure, another one is check for overturning, check for sliding. So check for bearing pressure used to done like this. So this delta CR, that is critical bearing pressure, which is to be arrived from the external force applied on the foundation, should be less than the bearing capacity of soil. The bearing pressure which is going to occur at the bottom of the foundation need to be calculated by these 2 equations according to the conditions applied. So the first condition is if actual eccentricity which we are calculating is less than the limiting eccentricity, then we need to follow this equation, that is P divided by A into 1 plus 6E divided by B. So here the P is a vertical load which is going to apply on the foundations. The A is the area of the pedestal area of the bottom slab, area in plan L into B. L is the length and B is the breadth of the foundation pad. Whereas that E is the eccentricity, calculated eccentricity, which is to be done based upon the moment applied on the foundation at the base divided by the total vertical load P. So that MO is a moment, calculated moment at the base of the foundations in kilonewton meter, which is to be calculated like a moment at the top of a pedestal or top of the foundations plus the horizontal force acted on the top of the foundation into the total height of the foundation, that is top of the foundation to the bottom of pad, that is Y bar we are assigning here. So that is a lever arm distance from base of the foundation to the pedestal top. So that we need to multiply with this horizontal force applied on the top of the foundations and adding to the actual moment at the top of the pedestal or foundations. Then we can find out the calculated moment at the base of the foundation. So this total moment, that is calculated total moment, to be divided by the vertical force, total vertical force P. So this vertical force means that total vertical downward load from the structure plus weight of the overburden soil plus self weight of a foundation. In case of block foundation, this weight of overburden soil will not come. Only the self weight of the foundation and the vertical download from the structure to be considered. So because of these reasons, the foundation sizes will get increased in both the plan area and the thickness of the depth in kind of block foundation compared to the isolated foundation, because the weight is, we are going to reduce the overburden soil weight. So this breadth, we already seen that it is a breadth of the foundation B, and the X is the contact length of the foundation base, which is having the equation as 3 into 0.5 L minus E is a eccentricity. So this equation we need to apply in the second equation of the ground pressure below foundations. If the actual eccentricity is greater than the limiting eccentricity. So limiting eccentricity is nothing but it is a B by 6 or L by 6, whereas B and L are the breadth and length of the foundation bottom pad, that is in meter. So any case, no case, this eccentricity should not go beyond B by 3, that is maximum eccentricity, B by 3 or L by 3 in meter. So in that case, it means the totally the foundation is collapsed. Then we need to provide the bigger size of the bottom pad length and the width, that is breadth, in order to reduce the eccentricity. So this horizontal force we have seen already while calculating this calculated MO moment. So these are the major parameters which we need required to calculate the bearing pressure at the base of the soil and check this base pressure compared to the soil bearing capacity, so that if the soil bearing capacity is higher than the calculated bearing pressure at the foundation due to the external force, then we can call it as this foundation is safe for bearing pressure. Also, alternatively, if the bearing pressure of the soil in kilonewton per meter square is not applicable or not available at the soil investigation report, then we need to go for alternative method in case of filled up soil. So in that case, we need to find out the net subgrade modulus K. So this is the equation we need to find out the net subgrade modulus wherever the foundation, if it is subject to various filled soil below the ground level or below the foundation top level, then we need to consider this. Whereas HI, so here that 1 divided by HI divided by ESI plus 1 divided by Km is a general equation. So that HI is a depth of fill material in meter, ESI is a elastic modulus of filling material, whatever the material we are going to fill below the foundation. Km is a final subgrade modulus of virgin soil in kPa per meter, which is arrived at the bottom of the foundations. So this detail about more detailed calculation we will be looking in the third stage, that is stability check. Also in the second parameters we are going to, in the second series of video, we are going to find out various filling materials according to their thickness and the how that net subgrade modulus to be arrived, that we are going to discuss in our parameters, that is in second series of video. So after finding this bearing capacity and checking with the soil bearing capacity, we need to find out the factor of safety by applying that bearing pressure of the soil divided by the cross pressure below foundation, as we calculated from these two equations as per these condition applications. So this factor we need to check with EN 1997 to find out the safety factor, so that we are going to check in we are going to discuss about the detail in this series of 3 about the stability check. And the next one is a check for sliding. So in this before that, check for overturning. So this overturning is very simple. We need to check this factor of safety should be greater than, by applying the resistant moment divided by the overturning moment, which is to be calculated from the moment at the base of the foundation, which we already calculated here for the bearing pressure. So this moment we need to check with the bending moment, that resistant moment of the foundation. The resistant moment is mr, which is nothing but the p is a vertical load, total vertical load as we have calculated here, into the width divided by 2. So this we need to find out the factor of safety, whereas this factor of safety should be greater than the expected factor of safety defined in EN 1997. So similar like the sliding also, we need to check that the total horizontal force at the foundation base should be lesser than the resistant force, the resistant force from the foundation and the sliding resistant due to the soil. So this sliding resistant we can able to find out as 5 into p. P is a total vertical load as we have seen in bearing pressure calculation, and HO is a calculated resultant force at the top of base of the foundation. So this phi is nothing but the coefficient of sliding between soil and concrete. How to find out this value is nothing but 0.767, that is two-thirds of the tan phi. So this phi is a 30-degree we are going to consider this for this calculation purpose. Generally this should be referred as per the soil investigation report, the angle of internal friction of the soil to be identified from the soil report, this phi value. According to this degree, this value phi will be changing, so that P is a total downward load. So in this case, for block foundations which is to be laid at the soil itself, we don't have any weight of overburden soil. So accordingly the factor of safety should be more than the expected factor of safety in year 1997. So this all stability check, that including bearing, overturning and sliding, we are going to look in the series of 3 of this video content. And next is a design of foundation, which is a fourth one, it is a fifth one series. And in this bottom pad we are going to design and check for punching shear. So these are the class we are going to find out in, we can discuss this in the stage 5 or series 5 of this video more detail. The brief discussion is that VED, which is a horizontal force developed, shear force which is developed in the foundation to be less than the VRDC. VRDC, the calculation procedure is here. We can see this 0.18 gamma C to be applied here. And these are the various ingredient which we need to find out from the EN 1992, that we can discuss more detail during the stage 6. And these are, next one is a check for one-way shear. So this is also we need to check according to the base slab foundation requirement, whether the thickness is sufficient to hold the one-way, check for one-way shear. So, and the final one is a design of a pedestal or column. So this slenderness ratio we need to check. Based upon that, there is a equation in class 15.8.3.1 EN 1992. The slenderness limitation is 10.78 square root of n. N is a relative axial force, which is equal to Pu divided by AC FCD. So the Pu and AC we need to apply based upon the actual dimension of the concrete pedestal and of the cross area and the load which is to be applied on the pedestal. So based upon that we need to calculate this, and alpha cc and fck, alpha cc is 0.85, fck and is a compressive strength of concrete, which we have going to consider the material parameters as C35, C25 bar 30, confirming EN 206. And the grade of reinforcement steel we are going to consider B500B, confirming to BS 446. So based upon this, this FCK we need to extract from this, and gamma C is a partial coefficient factor, as per EN 1992. So applying all this, we can able to find out the limiting slenderness. Also the actual slenderness we need to calculate from the height divided by the minimum dimension of the pedestal, so that it should be less than 3. If it is less than 3, then it is a cantilever column fixed at the base without with bottom subjected to bending, so we need to design accordingly, and the slenderness should be limited to this slenderness value so that the pedestal size can be adapted. So these are the overview. So in the next series onwards, we are going to look into that more detail about the calculation. Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.